Okay, good morning. My name is Fargüell, and I'm doing a PhD about computer science in the Computer Architecture and Operating Systems department in Universitat Autònoma of Barcelona, here in Spain. And I'm going to talk about the spatial and time resolutions, two critical aspects for operational forest fire spread simulation. Okay, first of all, as you know, the evolution of a fire depends on many factors, like vegetation, like slope, like the location, the first perimeter, and the initial characteristics of the fire, and the atmosphere that surrounds the fire. That also is really important, the effect from the fire to the atmosphere, as we will see. All of these things are really important, but also if we want to help the firefighters, we need to obtain results in an operational time. So we have to exploit computational resources and parallel paradigms. And our investigation is focused on that way. So if we see at the literature this feedback from between fire and atmosphere, there are two main strategies. The first strategy is I call them as a unidirectional strategy, and it's we pre-calculate the atmosphere state at different times, and then we use this information to propagate the fire. Another strategy is the bidirectional strategy. We have two different models, atmospheric and the evolution of the fire, and we share the information between these two models in order to propagate the information reliable. So, if we want to see the difference between these two approaches, we can see an experiment of a real fire here in Spain, 8th July of 2005, from 3 to 9 p.m. And we chose this experiment because it's strongly dominated by the fire winds. So we use these two different strategies in a first approximation. Here we can see in the green shape we have the real fire in its final state, and all the dotted shapes are simulations. So we can see that the direction of the fire goes in a wrong direction in the case of unidirectional strategy, because we are not capturing the effect from the fire that affects the direction of the wind. But also this affects a lot the execution time, the uses of one of other strategy, because we have to use a more complex model. So there are two lines of investigation. The first one is to try to improve the results in the unidirectional strategy, or the other is trying to speed up the bidirectional strategy, and we are in that way. As a test study, we use a simulator that couples the meteorological model WRF and the evolution of the fire model, that is SFIRE, with the coupling we saw. And it works if we draw a temporal line. We want to evolve the fire in each time step, dt. So we solve the meteorological model and use this information to propagate the fire using SFIRE. And we use the information from SFIRE to another time solve the meteorological model, and so on. WRF SFIRE uses as a basis the Rother-Melson empirical equation that has the wind and slope factors, and also the characteristic of the vegetation inside this R0 we can see. But this is a punctual propagation of a punctual spot, and we have to propagate a perimeter. So we need a method to propagate the perimeter. In the case of Warp Sphere, is the level set method that is solving this partial differential equation numerically. And if we see all the structure of Warp Sphere, first we solve this system of equations, that is the meteorological model. Do some interpolations vertically and horizontally, and propagate the fire using the things we saw just now, using different numerical methods. And with this, we obtain the fuel fraction in all the points and the time ignition in all the points in the domain. And with that, we can calculate the heat fluxes, and these heat fluxes effects on the meteorological model again, and so on. To represent the reality, Warp Sphere needs a 3D atmospheric grid and a 2D fire grid. And we use these two grids together in order to evolve our propagation, our fire. So we can define the fire resolution as the distance between two fire points, and the atmospheric resolution, the distance between two atmospheric points. Here we have two constraints from the literature. That is, at least we have to use 10 fire points for each atmospheric point, and we have to use time step in seconds less than 6 times the atmospheric resolution in kilometers. This is by for the convergence of the atmospheric model. So if we want to solve a fire in a resolution of 25 meters, this is an example, we have to use 25 by 10 250 meters in the atmospheric resolution, and the condition, the time step condition, it has to be less than 1.5 seconds. So we can see that if we want to use a high resolution, we have also to use a time step really low. So we are conditioned with that. So if we go back to the example, the data we used, the initial data we used is the elevation data is from the National Institute of Geography here in Spain. The vegetation is from a European project, the Corinne Land Cover, using a transformation to the 13 Rodermel models that uses Warp Sphere. And the shapes from the 5 factors of here of Generalitat de Catalunya. And we use the little one, the gray one, to initialize the fire, and the biggest one to compare with the simulation. And finally, the meteorological initial data from the meteorological local service here in Catalonia, Meteocat, at 3 kilometer resolution. So the first thing we have to do is interpolate all the data at the same resolution in order to have the initial data at the same resolution. And we propose the first methodology to take the file resolution at the same resolution than the initial data we use. This is here in each point of the file resolution we have an information in the initial data. So it's like the example. So the atmospheric resolution has to be at 250 meters, and the time step at 1.5 seconds less than 1.5 seconds. And this is the result using this configuration. We can see that we are underestimating the real fire. So we did some investigations trying to explain why we are underestimating the fire. And we saw that it's a problem that we are not representing well the meteorology, because we have to take more points to understand the effects from the fire to the atmosphere. So we double the resolution twice, and we obtain better and better solution. But the time it's also growing up really fast. So the execution time. So we use an intermediate solution also of 100 meters in the atmospheric grid and 10 meters in the fire grid, and we obtain more or less solution comparing with the other. And here we can see the wind speed and direction using the different configurations, using the different resolutions. And we can see that this is the initial data, so we can see that it's the same but draw it at different resolutions. But 5 hours later, we can see that using highest resolution, we are capturing the wind affected by the fire, because we can see here the green and yellow and red colors that are speeded winds, and we can see that are surrounding the perimeter of the fire. Here we can see also a 3D representation of that, and we can see the velocity of the wind going going up and in the perimeter of the fire. So this is a wind produced by the fire itself. But as I said, the time consumption goes up really fast. So we can see that the difference between the two last cases are really huge. And so we have to exploit our computer resources and parallel paradigms in order to, for instance, if we take this case, that it seems that it was the more balanced between accuracy and execution time. That is what we need. It's a trade-off between the execution time and the accuracy of the solution. If we take that, we can reduce the execution time using a multi-core first approximation. And so we can see that it's a line of investigation really open. So to summarize that, what we want to do is giving an initial state of the fire, initial state of meteorology, and the hardware we have, a specific hardware. We want to know which configuration of grids or time resolution we need in order to have an accurate and in a real-time solution. So thank you for your attention, and do you have some questions?